But just a reminder, don't forget to rate the sessions at shed.org. And if you have to leave or enter the presentation during the presentation, be considerate to the speaker. Try to do it as quietly as possible, okay? So we have Jakub Sitnicki here, and the name of the presentation is Scripting Your Network Benchmark Test with Lua. There you go.
Thank you. So hello everyone again, welcome. Thank you for coming. My name is Jakub, and I'm from the networking services team at Red Hat, where I work on the network stack and more recently also on software-defined networking in Oven project. But today I want to talk to you about tooling. I want to introduce you to a network benchmark we have been working on, a tool that you can extend and adapt to your needs using Lua scripting, a tool that we call Rushit. So let's start with why we decided to build a new tool. But first, just to be on the same page, a tool I will be talking about can be classified as a network microbenchmark. So what is a network microbenchmark? Well, it's supposed to generate an artificial network workload, and it's supposed to be simple, meaning less complex than a real-life distributed application, so that when using it, you can concentrate on the underlying network aspect instead of having to deal with the complexity of real-life apps. So it generates a workload, say it sends some TCP packets, and while doing that, it will measure how well it performs, how much work it can get done. And while doing that, it will collect some metrics, such as throughput, which you later use as input for tuning the underlying network environment. And there are really quite a few tools like that out there. Some of them are well known and have been around for a long time. If I had to guess, I would say that you have probably heard of used NetPerf or maybe iPerf or the new iPerf, but there are others as well. For example, how many of you have heard of FIO? Okay, yeah. It's a good benchmark, but it's mostly used for file systems. So a question comes to mind, why would we even need another tool, right? Well, all these network benchmarks and network applications in general, they do their work by talking to the network stack through the sockets API, or in general through a subset of syscalls. And if you're familiar with the socket API, you know that it has a lot of knobs and switches. It lets you configure your sockets in various ways, and this influences how particular layers of the network stack do their work. That's why the existing benchmarks usually have a rich set of command line options, so that you can tune and switch all those knobs. But as it turns out, they don't have all the knobs we need. So when I asked my colleagues what network stack features they would like to make use of during benchmarking, during the development of the network stack, let's say they had more than a few ideas. For example, we could distribute the load that comes into one port over multiple threads, or we could make use of low latency device pooling, or we can set up the TCP-X faster, or maybe we want to take advantage of warm CPU caches when processing incoming load. Or maybe we want to avoid a bunch of syscalls when writing from file or from memory. We can avoid destination lookups if we connect our datagram sockets. We can tell the TCP stack to send out a logical chunk of data all at once. Or we can tell it to send the data as fast as possible. We can make use of timestamping info. We can know when the buffer has been passed to the NIC. Or we can write our own programs to distribute the incoming load across CPUs in any way we want. We can configure the socket buffers and the related thresholds. We can open connections faster, finally, or look into additional info about socket that the kernel exposes to us. We can monitor the packet drops, or in some scenarios, we can even experiment with disabling the checksum computation. So, as you see, there are quite a few things we can play with, and they all influence how the network stack works. and hence how well it will perform. If you want to learn more about this, I can point you to these man pages and these two files in the Linux kernel where the option processing happens. So we more or less knew what to do. The next logical step was to take a look what is already out there and what we can maybe extend to fit to our needs. So I've taken a closer look at some of the tools that I mentioned before and some of the socket options they support. As you can see, there was a lot of red. There was not much support for all the things that we wanted to use. And it wasn't only in the socket option area. The support for the alternative syscalls for writing to the socket wasn't all that common. And some tools didn't even support the multi-threaded or multi-process model. So far, there wasn't a clear candidate for taking and extending, but we also taken a look at the code base and some subjective criteria that seemed important to us, like how complex the project already is. Does it have a non-conventional interface? Will we have to retrofit multi-threading to it? Finally, is it tried and tested? We couldn't really reach any agreement where to go with this, which tool to choose, and even if we did choose a tool, which features do we add to it, because we don't have time to add them all. That's when one of our colleagues suggested, well, why don't we build a tool that the user can adapt to its needs? A tool that you can extend by scripting it, so that we shift the burden of having to add support of new network stack features from the tool developers, that is us, to the tool users, that is you. And we like that concept because it means less work for us. So we went with it. Okay, so now let's talk a little bit about what we built. We didn't want to start from scratch, so we picked a project called Nepper as our base, as our network workload written in C. So Nepper originated at Google, who open sourced it around 2 years ago. And it seems to be inspired somewhat by netperf, we don't know, but the command line naming is similar, and the name seems to be a clever wordplay on the word netperf. But in contrast to netperf, it has a design that resembles better modern networking applications. Namely, it's multi-threaded, so we can have multiple server or client workers, and each worker can handle multiple flows, multiple sockets. That is thanks to the event-based main loop that pulls all the socket descriptors for events. What's important to us is also that it has a clean and small code base, but that is partially to the fact that it doesn't come with too many features. Originally, it came with only TCP workloads, and only recently we added UDP workload to that as well. A couple words about its interface. Different from existing applications, there is a separate program for each type of workload you would like to generate. So we have a TCP strong program for bulk transfer over TCP, which would be an SCP-like type of workload. Or you have TCP-RR for HTTP-like workload, doing request-response transactions. And finally, the newest one, UDP stream, that is supposed to resemble audio or video streaming. Similar to iperf, each program is dual mode. So depending on the command options you pass to it, it can act either as a server or a client. It's quite flexible in regard of configurations we can run it in. So the simplest, most basic one is just one server process, one client process, each running one worker thread, and one connection in between them, one network flow depicted by the red line. This happens when you start it with the default command line options like shown below. We can complicate it a little bit and ask it to open 2 connections from client to server by specifying the total number of flows on the command line. We can make it even more complex by having multiple threads running in each of the process. The numbers don't have to match on both sides. But as in this case, if there are more clients than servers, some of the server threads will have to handle more than one incoming connection. And finally, if we want to complicate it even further, we can have more than one client process talking to the same server. And in this case, we have to tell the server how many clients to expect, because normally it will exit after handling the first client. Okay, so that was our base, but we wanted our tool to be scriptable, so we had to pick a scripting language and an engine for the scripting language. And what we chose is Lua JIT. But first, let's talk about the scripting language we chose. We chose Lua, which is known to be simple and concise. So if you don't know it yet, don't worry, because there are tutorials out there that will get you to the level of writing your first scripts in a matter of minutes, literally. There's also a pretty good chance that you might know Lua, because it's quite popular for embedding in applications, perhaps most popular in games, but also in some network applications like Nginx web server, or some well-known network tools like the Wireshark packet analyzer, or the Nmap scanner. It also has a nice C interface. If you have ever used Java native interface, it's simpler than that. And it also runs extremely fast. The implementation we've chosen, Lua JIT, is a unique tracing just-in-time compiler, an amazing project which I highly recommend looking into if you don't know it yet. Finally, we can easily interface from Lua to C, calling C functions, which is very important to us. That is thanks to a FFI library, which we feed our C declarations of functions and data structures to, and we get our bindings down automatically. Talking about bindings, that's the last component we needed. We needed our scripts to talk to the system API. And for that, we reused a project called LJ-Syscall, which gives us wrappers for all the system functions known as syscalls usually, and all the constants and data types that are also part of the interface. It's an actively maintained project with a nice test suite that assures its quality, so perfect. The only thing that might surprise you is the non-C-like naming, but we create convenience aliases so you don't have to look up every constant you want to use in your scripts. Okay, so these are all the components of our tool. And the last piece, the missing piece of the puzzle, is your script. Let's talk about that. So first, a top-level concept. What we wanted to do. A user creates a script, feeds it to the program, the main thread runs it inside its embedded scripting engine, and delegates parts of a script that we'll call hooks to the worker threads that generate your network workload. Each worker thread has its own instance of a scripting engine embedded in it, so while executing the workload, at well-defined points, it will call the script chunks that we call hooks. That's the concept. It will become clearer as we take a look at the script. So how the script is usually structured? We have 4 parts. First one, the initialization, where you declare your top level, or define your top level variables that you'll later on use throughout the script. Then you have the meat of the script, the hooks. So chunks of Lua that you would define and register to be executed together with a workload. Then you have the second 2 parts, which are not always needed, but we can have a synchronization point, which will tell the engine to block there and wait for the workload to stop running and finish its work, so that you can collect the data from the hooks and do any kind of calculations or post-processing on it in the last part. So here's a small but fully functional example that you can run with this tool. Oh, sorry about that. I guess we need to take a break. First part, so what it will do? It will collect the socket file descriptor numbers that the workers will open and print them. So nothing fancy. So first part, we define our top-level variable and initialize it to an invalid value for a file descriptor, which is -1, and we mark it for collection so that we tell the engine to grab all the values from all the workers and aggregate them so that we can process it at the end. Then we have the main part of our script. We defined a hook, which will be called right after opening the socket. This is what we call a socket hook, and it has a well-defined interface. The first argument that it accepts is the number of just opened socket, which will just store it for later processing. Then we register the hook both on the client and the server side. We tell the workload to run, and we block until it finishes. The engine collects the data for us and puts it in the variable we declared earlier so that we can print it out. So how does it look when we run it? Well, if we start a server with 2 threads, somewhere in the output we'll see 2 sockets file descriptor numbers printed out. Same on the client side, but this time on this side we have 3 threads, so we expect 3 numbers. And you can confirm it with strace that these are the same numbers as the sockets that were opened. Okay, so we know that we can run chunks of Lua. Now, at what points of the workload we can run them? We have 2 classes of hooks at the moment. First class is tied to the life cycle of a socket, and we can register a hook to be run either right after opening the socket or right before closing the socket. But then we also have what we call packet hooks, which are tied to the state of the socket message queue and error queue. And in that class, we can register a hook to be run when the socket is ready to be written, send message hook, or when the socket is ready to be read from, the receive message hook, and finally when the error queue is ready to be read from, the receive error hook. How does it look when you put it all together and look at the program flow? So on the client side, the client will open the socket, then it will tell its engine to run the socket hook. When that is done, the client will connect the socket and move on to polling it for events. When the socket is ready to be written to, the client will execute the send message hook. The hook is in charge of writing the message to the socket. And at some point, the client will decide it's done generating the workload and it will stop. At which point, before closing the socket, it will call the close hook. Similar on the server side, we open the socket, we call the socket hook, we do a passive open, we monitor the socket for events. When we can read from the socket, we call the receive message hook, the hook reads out data, server at some points has to stop, so it calls the close hook and closes the socket. Simple. Finally, let me talk real short about 2 concrete use cases. So what for we can use that actually. So in the network benchmarks, you will see a code like that usually that will configure a socket to disable the naggle algorithm on the TCP sockets. It will just call setSock option with TCP no delay. And this is what will happen when you invoke netproof iproof with these flags. If we wanted to do an equivalent thing in Rashid script, this is how we would done it. We would define a hook to be called after opening the socket that will call setSock opt for TCP no delay. When we defined our hook, we'll register it to be executed both by the client and the server. And that is all. We run our tool, we feed the script to it, and we run our workload with naggle algorithm disabled. Again, you can do an strace and confirm that setSock opt has been called. So this was an example for a socket hook. Now let's take a look at another example for a packet hook. This time what we want to do is we want to check the sender's address of a datagram. So we register and define a hook at the same time for when we are ready to read out from the socket. We call receive from, but we also pass to it a sock address in data structure so that we can get the sender's address. Then we compare the sender address to the one we expect it to be, and if it doesn't match, we bail out. So what happens when we run it? Well, this time we just run it on the server side. We pass the script to it. The server will start. We'll wait for the clients. So we start the client, but we tell it to bind to an unexpected address. When the client starts sending the packets, the server will receive one. The address won't match, so the server will complain and bail out, while the client will report a bunch of errors because it has nowhere to send packets to because the server is gone. Okay, so we have been working on it for a few months now. The repo is already on GitHub. The link and the code will lead you to it, along with some documentation that will help you get started, and a bunch of examples which we hope you can adapt to your needs. We would like to continue to improve it, make it more user-friendly and suit your needs better. So this is a great time for your ideas if you want to help or contribute. The best way to do that is by opening an issue or a pull request on GitHub. Finally, I couldn't have done it alone, so thank you to my team for being the think tank for this project. And thank you for listening. If you want to get in touch after the presentation, here is some contact info. Thank you.
Do you have HTTP support or
SSL? The question was, does it have support for HTTP or SSL? Okay, so the workload we generate, it's on the transport layer. So you would have to implement that on top. It doesn't come with support for either HTTP or SSL. Thank you.
Oh, this is really interesting.